The dynamics then tells you why the object goes up, why the object goes down, why is it pulled down, and so on. That's dynamics. The reason it comes down is gravity is pulling it. In kinematics, you don't ask the reason behind anything. You simply want to describe things the way they are. And then dynamics tells you how they change and why they change. So I'm going to illustrate the idea of kinematics by taking the simplest possible example. That's going to be the way I'm going to do everything in this course. I'm going to start with the simplest example and slowly add on bells and whistles and make it more and more complicated. So some of you might say, well, I've seen this before, so maybe there is nothing new here. That may well be. I don't know how much you've seen, but quite often the way you learned physics earlier on in high school is probably different from the way professional physicists think about it. The sense of values we have, the things that we get excited about are different, and the problems may be more difficult. But I want to start in every example, in every situation that I explained to you, the simplest example, then slowly add on things. So what we are going to study now is a non-living object, and we're going to pick it to be a mathematical point. So the object is a mathematical point. It has no size. If you rotate it, you won't know. It's not like a potato. You take a potato, you turn it around, it looks different. So it's not enough to say the potato is here. You've got to say which way the nose is pointing and so on. So we don't want to deal with that now. That comes later when we study what are called rigid bodies. Right now, we want to study an entity which has no spatial extent. So it's just a dot. And the dot can move around all over space. So we're going to simplify that too. We're going to take an entity that lives along the x-axis. It moves along a line. So you can imagine a bead with a wire going through it, and the bead can only slide back and forth. So this is about the simplest thing. I cannot reduce the number of dimensions. 1 is the lowest dimension. I cannot make the object simpler than being just a mathematical point. So then you got to say, what do I have to know about this object at the initial time? What constitutes the present? Or what constitutes maximal information about the present? So what we do is we pick an origin, we call it 0. We put some markers there to measure distance. And we say this guy is sitting at 1, 2, 3, 4, 5. This is sitting at x equal to 5. Now, of course, we got to have units, and the units for length are going to be meters. The units for time will be second. And time will be measured in seconds. Then we'll come to other units. Right now in kinematics, this is all you need. Now, there are some tricky problems in the book. Sometimes they give you the speed in miles per hour, kilometers per year, poundals per square foot, whatever it is. You got to learn to transform them. That I won't do that. I think that's pretty elementary stuff. But sometimes I may not write the units, but I've earned the right to do that, and you guys haven't. So you still have to keep track of your units. Everything's got to be in the right units. If you don't have the units, then if you say the answer is 19, then we don't know what it means. Okay, so here's an object. At a given instant, it's got a location. So what we would like to do is to describe what the object does by drawing a graph of time versus space, and the graph could be something like this. You got to learn how to read this graph. I'm assuming everyone knows how to read it. This doesn't mean the object is bobbing up and down. I hope you realize that. Even though the graph is going up and down, the object is moving from left to right. So, for example, when it does this, it's crossed the origin and is going to the left of the origin. Now, it's to the left of the origin, it turns around and starts coming to the origin and going to the right. Okay, that is x versus t. So in the language of calculus, x is a function of time, and this is a particular function. This function doesn't have a name. There are other functions which have a name. For example, this is x equals t, x equal to t squared. You can have x equal to sine t and cosine t and log t. So some functions have a name, some functions don't have a name. What a particle tries to do generally is some crazy thing which doesn't have a name. but it's a function x of t. So you should know when you look at a graph like this what it's doing. So the two most elementary ideas you learn are what is the average velocity of an object. That's denoted by the symbol v bar. So the average is found by taking two instants in time, say t1 and later t2. And you find out where it was at t2 minus where it was at t1 and divide by the time. So the average velocity may not tell you the whole story. For example, if you started here and you did all this and you came back here, the average velocity will be 0 because you start and end at the same value of x. You get something 0 divided by time will still be 0. So you cannot tell from the average everything that happened because another way to get the same 0 is to just not move at all. So the average is what it is. It's an average. It does not give you enough detail. So it's useful to have the average velocity. It's useful to have the average acceleration, which you can find by taking similar differences of velocities. But before you even do that, I want to define for you an important concept, which is the velocity at a given time. So this is the central idea of calculus, right? I'm hoping that if you learned your calculus, you learned about derivatives and so on by looking at x versus t. So I will remind you, again, this is not a course in calculus. I don't have to do it in any detail. I will draw the famous picture of some particle moving, and it's here at time t, at some value of x. A little later, which is time t plus delta t. So delta t is going to stand always for a small, finite interval of time, infinitesimal interval of time, not yet 0. So during that time, the particle's gone from here to there. That is x plus delta x. And the average velocity in that interval is delta x divided by delta t. Graphically, this guy is delta x, and this guy is delta t, and delta x over delta t is a ratio. So in calculus, what you want to do is to get the notion of the velocity right now. We all have an intuitive notion of velocity right now. When you're driving in your car, there's a needle, and the needle says 60. That's a velocity at this instant. It's very interesting because velocity seems to require two different times to define it, the initial time and the final time. And yet you want to talk about the velocity right now. That is the whole triumph of calculus, is to know that by looking at the position now, the position slightly later, and take the ratio, and bringing later as close as possible to right now, we define a quantity that we can say is the velocity at this instant. So v of t is the limit delta t goes to 0 of delta x over delta t, and we use the symbol dx dt for velocity. So technically, if you ask what does the velocity stand for, it stands for, let me draw a general situation. If a particle goes from here to here,